All right, so today we're talking about spheres. And like I said, spheres are basically just three-dimensional circles, if you want to think about it that way. Okay, so in a sphere, right, each one of these guys right here, which we will call a great circle. These great circles, right, essentially just are all over the place in this thing. They kind of drive it. Now, if we think about it this way, kind of think about the Earth, right? How many of you guys know about lines of longitude and latitude? Right? Why do we use the poles as kind of that one place?
They're like the very top.
Right, they're at kind of like the very top. But kind of this is kind of why. So if I imagine drawing just an infinite amount of great circles, right, to the maximum, the largest possible circle that I can fit on this around this sphere, right? If I just kind of draw them, like keep them, I guess not parallel, but if I just kind of keep drawing them, right, all along, right, you'll see that they start forming, right? They start touching in two places, each of these poles. Okay. So I know that that's not really helpful for necessarily understanding surface area, but this is just to kind of give you an idea of what we really consider like a circle, right, on a sphere. Right? These are the main components. Now, each one of these, right, they're all going to be the exact same size. It's kind of why it makes a sphere uniform. Now, each one of those great circles is still a circle, so it has what we call a radius. Okay? And each one of these radii, right, are essentially the radius of the sphere. Because they're all, again, all the circles are congruent, so therefore all their radius or radii are congruent, which meaning that if I draw a point from the center of this sphere, right, to any point on the sphere, right, it's going to be the same distance away. Right? So that's what we call our radius. Okay? Now, to come up with surface area, all right, I want you to look at a sphere just a little bit different. So understand, the spheres are a lot more complex in terms of understanding how to find the formulas for these guys. Okay, so we're going to look at this in more of a general kind of sense, and then you'll kind of see where it at least comes from, but we won't really focus on the math behind it. Okay, so when you're looking at a sphere, if you think about everyday objects that you see as spheres, okay, and if you play a sport that has a ball, you're playing with a sphere. Okay, most of the time, unless you're playing football. Okay, but almost every single ball is spherical in shape. Hold on a second, someone's talking to me. You still can't see what I'm doing? Those of you on Zoom, I'm sharing. I'm not actually writing anything on here at the moment. Malachi, you're on the Zoom, right? You can see it? Okay. All right. So maybe John either leave and come back or go ahead and reset yeah. Okay. All right. So for surface area, we're going to look at this again. You can look at this several different ways. Or we could try to break up a basketball, for example, right? But the easiest way to kind of see where the formula comes from is through a baseball. Okay. So how many of you have ever played baseball or even softball? It's the same kind of idea. How many of you have ever held a baseball or a softball? Okay, so you understand what I'm talking about when you kind of look at the surface area of this thing. All right, it's made up of two leather patches, right? They kind of look, I guess you could say, saddle in shape. Okay, so if I just unraveled this baseball here, right, what it would kind of look like. And again, this is a horrible drawing, right? A horrible drawing, right? So that would be one piece, and then you'd still have the second piece, okay? So it's made up of two, essentially, leather patches, okay, that look like this. Now, to kind of calculate the surface area, all right, if I imagine each one of these parts, right, and I imagine kind of the great circles that go around this ball, right, you'll see that the stitches don't quite create a great circle, which means they don't go around, right, at the largest possible circle on this thing, right? It's a lot smaller. Okay? So what this thing essentially creates, right, is 4 circles that are just a little bit smaller, right, than the great circle of the sphere. Right, this overlap here is intentional, by the way. Okay. Now, if we kind of just think about these as parts of the great circle, that means that each one of these circles would have a radius r. Right? Why is everyone so late? Okay. So, each one of those would have radius r's, and you can see that there's essentially 4 circles in here. Now, again, we haven't taken into account these 2 areas yet, and that's kind of where the math gets very, very complicated, okay? So imagine essentially if we kind of stretch these circles, right, these 2 parts, and we kind of tried to fit them into the circles, right? That would mean less and less material on these guys, because again, I'm stretching this thing to meet this circle, right? And I'd be pulling away at it, it'd be getting smaller and smaller. And so the idea behind this is if I pull hard enough, essentially what's actually going to happen, and math will show this, right, is that I've got enough to fill exactly 4 great circles. Okay? And if each one of these, right, each one of these circles has an area of pi r squared, right? And if I stretch all the material enough to create those things, what do you think the total surface area of this object is going to be? Well, how many great circles are there? And what's each one of their area? Pi r squared. They're all congruent, right? So the surface area for a sphere, right, is always going to be 4 pi r squared. Okay. And again, I know that may not make the most sense, right, but this is the kind of one of the better ways I can visually show you guys this. So now applying that, okay, so the surface area is 4 pi r squared. So we're going to look at an example. And again, best example of a sphere that we have is a globe. And yes, I do not subscribe to flat earth theory, just to let you guys know. Okay. So when we're going to look at, again, surface area for a cube is 4 pi r squared. Okay. So the globe below is spherical in shape. Okay. It has a radius of 6 inches. Okay. We're going to do this in 2 parts. We want to find the total amount of material needed to create the globe, assuming it is hollow, okay? And then we want to know how much material would it be needed to make each hemisphere, okay? And we'll talk about that in a second. So let's just do part A, okay? Find the total amount of material needed to create the globe, assuming it is hollow, okay? Again, that's kind of our idea of what surface area is. If I wrap a box up, it's how much wrapping paper would go around to cover the entire box. Okay, so if we're thinking about this globe, we're thinking about the material, it's all the material to make exactly a sphere. Okay, and it would encompass the surface area. So the surface area, right, so in order to find how much material we would need, right, since we would find the surface area of the sphere, which is 4 pi r squared. Okay. Now, the only variable we need in here is what the radius is, and we're given it as 6 inches. Okay. So in order to find my surface area, it's just 4 pi times 6 squared. Okay? So we now have 4 pi times 6 squared. So this is 4 pi times 36, which is equal to 144 pi, right? And so this would be our exact answer. Our exact answer is 144 pi square inches, okay? But, right, if we want to think about approximate, because again, how do I cut exactly 144 pi inches using scissors, for example, if I want to cut wrapping paper? Right, it doesn't really work. So that's why we approximate this thing, right? And if we approximate this thing, this is essentially the same thing as 144 times 3.4, right? Approximately 144 times 3.14. Oh, goodness. Which is approximately 452.16 inches squared. And so that's how much material of whatever we're using it would take to encompass this whole sphere. Okay? Again, assuming it's hollow. Now, for part B, okay? For part B, I can't talk. For part B, how much material would be needed to make each hemisphere? And so the whole reason that I wanted to do this part of the problem is because I want you to understand what a hemisphere is. Okay? A hemisphere is exactly what? It's half a sphere. Okay? It's exactly half a sphere. Now we need to be careful here. Okay? So for this case, since we're not going to be covering underneath, and I'll explain that in a second, right? In order to find the surface area of the hemisphere, right? It's exactly half, right, of the surface area of the entire sphere. Okay? So if I wanted to find the surface area of a hemisphere, it'd simply just be 2 pi r squared. Okay? But I don't want you to memorize the formula for a hemisphere. I'd like you to think more in terms of the fact that it's exactly half a sphere, and I'll explain why in just a second. Okay? So for this case, yes?
You just divide 450.
That's exactly what we're going to do. Okay? So, and that's why I want you to think about it this way. Okay? So instead of trying to think about it as a formula, right, we know that our entire sphere, right, has an area of 144 pi inches squared, and so all we're going to do is divide that by 2. Okay? Or we're going to approximate it as 452.16 divided by 2. Okay? And so we can either get, say, 144 divided by 2. So we could either get 72 pi inches squared, or we can get 226.08 inches squared. Okay. Now the reason that you need to be careful, and I don't want you to think about the formula for a hemisphere, is there's 2 different essentially types. Okay? So let's just say I have this hemisphere here. Now, if I wanted to just think about, hold on, if I wanted to just think about the shell, okay? So think about it like kind of like the top of a turtle shell, right? Then the area of that part would be 2 pi r squared. Okay? It'd be exactly half of a sphere. Now, if I wanted to instead, got another hemisphere. Okay? if I wanted to instead include, right, so wrap this entire thing up, right, so that means cover the bottom, I would need to include the base area. Okay? So this formula works for only the top. This formula works for all surfaces. Right? So if I imagine kind of covering up, like there's a circle on the bottom of this thing. So think about like there's certain types of snow globes, right, which are only little half globes, but you can set them down and they've got a circular base and stuff like that. That's kind of what we're talking about here. Okay? So if I wanted to do it for this one, it would be 2 pi r squared plus the area of the circle underneath, which would be pi r squared. Or 3 pi r squared. Which I know sounds weird, right? So that's why I didn't want you to think about hemisphere in terms of formulas. Try to think more about just solving the problem. Okay? Does that make sense? Okay. So now, for volume, it's going to be a lot more complicated. Okay? I will be posting these notes, by the way, just to let you know. So volume, it's going to be a lot more complicated. So I'm actually going to pull up a GeoGebra here. Whoa, sorry. I don't know why it's doing that. Come on. All right. No, I'm not trying to type in here. Okay. So here I have a sphere. Okay. Now, if I wanted to try to figure out the volume of this thing, okay, what I would do, right, is one of the things that I could do is I could draw essentially. This thing is being very wonky. Okay? You could draw essentially and create a pyramid inside of this thing. Okay? Because that would be a good way, because I can do volume of pyramids, right? So, for the volume of each pyramid, it's base area times height over 3. Okay? Now, in this case, right, if I'm looking at the height of each pyramid, okay, we can see that again. What we're going to try to do is we're going to fit an infinite number of these, right, very, very small pieces. We're going to make these, so yes, we're doing a square pyramid, but what we're going to try to do is create this sphere out of square pyramids. So I'm just going to take a bunch of them and just kind of put them inside this thing. And they're all their top points are going to meet at the center of this thing. Okay? Which means, right, that the height of each of these pyramids is essentially going to be the radius of the sphere. That's what we're going to get to. Okay? Now, if we added up, so again, we made these infinitely small pyramids. If we added up all of the bases, right? If we added up all the bases for all the ones that would use to create the sphere, we would have the total surface area of the sphere. Okay? So the sum of all the bases of all the pyramids that we could kind of make in here. And again, like this is a rather large, it won't let me like do what I want to do with this. It's being really dumb. Okay? If I take this point A and I make it really small, take B and I just kind of keep making these smaller, or oh my gosh, stop moving the whole thing. It's being really touchy right now. Right? And essentially just make a bunch of infinitely smaller square pyramids, right? So the smaller and smaller my square pyramid gets, the closer and closer to approximating this thing actually gets. Okay? So, if I add up all the bases, if I make an infinitely small number of pyramids, if I make the pyramids, their bases infinitely small, but even still I added them all up together, I would still only get the surface area of the sphere, which is 4 pi r squared. Okay? So now, so if I have 4 pi r squared, right, times, that's the base area, the total sum of base areas, right? Times the radius or the height of each of these spheres or each of these pyramids, and divided by 3. This equation right here, this 4 pi r squared times r over 3, right? This gives me, right, the total volume for all of the pyramids. Okay? Now, when we simplify it, right, and just multiply the r, we get 4 pi r cubed over 3. So this is actually where the volume of a sphere comes from. So the volume of a sphere, the formula for it is 4/3 pi r cubed. Okay? It's 4/3 pi r cubed. Again, I apologize for the visual. It was supposed to be better, but it just did not cooperate very well. Okay? So the volume of this guy is 4/3 pi r cubed. Okay? So now let's apply it to a real world situation, remembering that 4/3 pi r cubed. So let's just say you're creating a spherical snow globe with a radius of 4.8 inches. Okay? Key part here is the radius. Okay? How much liquid would you need in order to fill up the snow globe entirely without any excess? Meaning, no bubbles, nothing. Okay? So if we're thinking about that, right, it's kind of like the whole cylinder thing of how do we find the volume of a cylinder? Well, we just think about how much liquid is in a can. Okay? So it's going to be the exact same thing for filling out or finding out how much liquid we're going to throw into this snow globe. Okay? So we need to calculate its volume. Okay? So for the volume for this guy, all right, since it's 4/3 pi r cubed, and I know that my radius is 4.8 inches, okay, my volume is just simply going to be 4/3 pi times 4.8 cubed. Okay. Now I know that looks like a very complicated problem, so we're going to go ahead and use, if I can find it, Desmos. Okay. So for Desmos, we're going to go 4/3 pi times 4.18? 4.8, right? Cubed. Okay. And we get that. What is that? Does anyone hear that humming? Is that coming from outside? Can you please shut the door then? What? Well, try shutting the door, see if it helps, because that is driving me nuts. Oh, sweet reprieve. Okay. Whew. Anyway, all right. So our solution now is, since it's 4/3 pi r cubed, r was 4.8, we get 463.25 cubic inches. Okay. So our volume is approximately 463.25, and since we're doing with inches and volumes is always cubed, our volume is 463.25 inches cubed. Okay. Any questions on this? No? Okay. I know I kind of threw a lot out of you, and I know visually it's kind of hard to understand sometimes. All right, so that's why I would just kind of focus on the formulas, so to speak, and just kind of apply what you know. So what I've also done, if you go back to that Google slide, all right, so you go back through that Google slide, okay. Oh, I forgot to go over this. All right, this is kind of what we talked about at the beginning. Right. What I've done is I've actually given you a list of all of the formulas that we have talked about so far. Okay. So, if you go back to that Google slide at the very last slide, right, should be a list of all the formulas that we talked about. And yes, on your test on next time, you are allowed to use this. Okay? You are allowed to have this. Are there any questions?
Yeah, how do you access this?
What's that?
How do you get this again?
So it's under modules in Canvas, and it should say like, I think it just says 3D objects or three-dimensional objects, and then it should say like presentation or something. I'll help you find it in just a sec, man. Okay. But yeah, if you have any questions, please feel free to let me know. I'm gonna go ahead and stop recording.